Alright, geometry students, welcome back to another Regents review video. This is the Geometry Common Core Regents exam, June 2017. These are the short answer questions. These are the tough ones that everyone who took this exam back in June of 2017 had trouble with. These are going to be the solutions to parts 2 through 4 of this exam. And make sure that you have your calculator ready and make sure that you have your brain turned on and working, because some of these questions were definitely tricky. And let's just go through them before we begin. As usual, do not under any circumstances take this information and put it on a piece of paper and call it your own. Make sure that you're here to work. Make sure that you're here to learn. If you are here to copy my answers, you're not doing the right thing. You're going to make me disappointed. Or you're going to you're going to disappoint me, and you're going to disappoint yourself when you get your score back. So please try the problems on your own. Here we go. Without further ado, let's go to the part 2s. The first one's a construction. So real quick, as if you've been watching my videos throughout this entire review process, understand that I show the construction here on my computer software. Then I jump to a hands-on version of the construction. So if you want to see it this way, fine. If you want to see it as if you were to actually hold a compass, that's the next section. Here we go. Number 25. Given trapezoid JKLM with JK parallel to ML, using a compass and straight edge, construct the altitude from vertex J to line ML. Well, the first thing that I need to grab is a straight edge, and I need a compass. Perfect. So what we're going to do is we're going to construct the altitude. Now, you have to remember what is the altitude again? Well, the altitude is perpendicular to its base. Whatever it is. It could be a triangle, it could be a trapezoid, it could be a parallelogram, whatever it is. And altitude is drawn perpendicular to its base. But in this case, we're drawing it from J to ML. So we need to use some basic knowledge of constructions to get this right. This is a classic example of a perpendicular line, drawing a perpendicular from a point not on the given line. The given line in this case is actually ML, so we actually need to construct a line that's perpendicular to ML from point J. Well, how do we do that? I'll show you. The first thing that you're going to do is you're going to take your compass and you're going to place the compass point on J. Or if you're using a safety compass, you place the plastic piece that swivels on point J. Now, what we're going to do is we're going to then extend our compass a little bit more, or a little past line ML, but enough that we could actually swing the compass in both directions and intersect line ML at 2 points. The 2 points of intersection are here and here. If you expand your compass too far, you're going to miss. It might make an arc over there. You got to go smaller. So now what I'm going to do is I'm going to not change my compass setting. And what I'm going to do is I'm going to swing above and below using these 2 points on our line. So I'm going to place my compass point on this left point. I'm going to swing below, and I'm going to swing above. Then I'm going to repeat the process on this blue dot. Swing below and swing above. There we go. And swing above. Now, here's the thing, folks. You don't have to swing above. You could actually just swing below and you'll get credit anyway. But I like to be accurate. I swing both above and below. Now, the last thing to do is just take your compass, your straight edge, and you are going to simply connect these 2 intersection points. So place your straight edge on that intersection point and that intersection point right over here. And you are just going to draw, you're going to draw that line. Just like so. There it is. And that, ladies and gentlemen, is a altitude drawn from vertex J to ML. Now, we're going to go through this construction again if you want to, using a hands-on construction. If not, you can just fast forward the video. Okay, this is question number 25 from the June 2017 Regents exam. This is the construction that is hands-on if you do not like the computer software that I use. So, the question says, given trapezoid JKLM with JK being parallel to ML, using a compass and straight edge, construct the altitude from vertex J to line ML. Leave all construction marks. So remember that by definition, an altitude is perpendicular to its base. So our goal is to create a line passing through J that's perpendicular to line ML. Well, how do we do that? Well, we need to understand that in order to complete this construction, we need to place our compass point on J and measure to the length of ML. This is a classic example of a point not on the given line, and your goal is to construct a perpendicular. So I'm going to place my compass point on J, and I'm going to extend my compass a little past ML. So that is slightly past line ML. What I'm then going to do is I'm going to construct an arc. What this does for me is it gives me 2 points or 2 reference points that I could use to generate my perpendicular line. Then I go back to my compass. I then place my compass point on these 2 intersection points, and I swing my compass above and below. So let me just move this up a little bit. Okay. And then I'm going to construct below, followed by an above arc. Now, you don't have to do the above arc. You could actually just do the below arcs, and you would still get full credit. And I'm going to repeat the process on this point. I'm going to go below, and then I'm going to go above. As you can see, I have 2 intersection points. I personally like 2 intersection points because it is more precise, but you could have just drew one of these arcs. That's perfectly fine. And then you just construct or draw your line through these 2 intersection points, and it has to pass through, remember, it has to pass through point J. And that is how you construct an altitude from vertex J to line ML. All right, here's question number 26. Determine and state, in terms of pi, the area of a sector that intercepts a 40-degree arc of a circle with a radius of 4.5. First thing that I want to do, draw a picture. It's always nice to draw a picture. So here's my circle, and what it's saying here is we are drawn from the center of the circle to the outside, or something like this, like a pizza slice. And it tells us that the angle intercepts a 40-degree arc. So this arc right here is 40 degrees. So this angle is intercepting this arc. And find the area of the sector. And the radius is 4.5. So 4.5. Well, you need to know what the area of a sector formula is. There are actually 2 ways that you could do this. I use it this way, then I'll show you the other way. The area of the sector of a circle, the formula is given as n over 360 pi r squared. Okay? So the n in this case represents the central angle. N represents the central angle. And the central angle is the angle that intercepts this 40-degree arc right here. So this angle, which is a central angle because it is in the center of the circle, is 40 degrees. Okay, plug it in. So the area is equal to 40 over 360 pi times the radius, which is 4.5, and you square it. Now, what I'm going to do is I'm going to type this information into my calculator. Only the blue. I'm going to leave the pi out because it specifically says in terms of pi. So I'm going to go to my calculator. TI Inspire calculator. Pretty good. 40 over 360 times 4.5 squared. Yes, it is. Okay. And you get 2.25. Fantastic. So the area of the sector is equal to 2.25 pi. That's one answer. Now, you could even express this as a fraction. You could have said the area is equal to 9/4 pi. That's perfectly acceptable as well. Now that I'm thinking about it, I am not going to show you the other way to solve this problem. I will tell you that the other area formula, because there's two formulas, the other area formula is A equals 1/2 r squared theta. But if you don't know how to use that one, forget that I just said that. That formula will come useful in later Regents exams or even earlier Regents exams. You might see a pop up here and there, but those formulas could both be used interchangeably. Number 27. Oh boy, I remember this one. The diagram below shows two figures. Figure A has or is a right triangular prism, and figure B is an oblique triangular prism. The base of figure A has a height of 5 and a length of 8, and the height of prism A is 14. The base of figure B has a height of 8, length of 5, the height is 14. Okay, fine. Use Cavaliers Principle to explain why the volumes of these two triangular prisms are equal. When people took this exam, they didn't know what Cavaliers Principle was because this was the first time that the state of New York was testing it. So, this is, I'm going to talk for a little bit. I'm going to lecture to you. This is what Cavaliers Principle states. If you have two prisms, it doesn't matter what prism it is, it can even be a cylinder, okay? The perfect example that I'm thinking of for cylinders is a stack of quarters, okay? If you have 10 quarters side by side, and you take one of the stacks and you simply push against it, it will form an oblique cylinder. It will look something like this, right? It will look something like this. The quarters will be leaning on its side. Of course, not that dramatic, but the quarters will be leaning on its side. Does that have the same volume as the quarters next to it? They're both 10 quarters. Do they have the same volume? Do they take up the same amount of space? Yes, they do. And that's what Cavalieri stated. He basically said it doesn't matter how you orient or push the prism, it still takes up the same amount of space if the heights are equal and the base areas are equal. So I'm going to put that into words. We're going to talk about it, and we're going to finish this problem. Here we go. The first thing, the first step that you got to figure out is you need to calculate the area of both of the bases to prove that they are the exact same area. So these are both triangles. So the area formula of a triangle is 1/2 base times the height. In this case, the base is 8 and the height is 5. Okay? So the area of this triangle is equal to 1/2. The base is 8. The height is 5. The area of the triangle is equal to 1/2 times 40. 8 times 5 is 40. 1/2 of 40 is 20. So that's the area of this base of figure A. Let's figure out for figure B. So the area of the triangle is still 1/2 base times the height. It's still a triangle. In this case, the 5 is the base. The height is your 8. The area of the triangle is equal to 1/2. The base is 5. The height is 8. As you can see, it's the exact same thing over here. It's just swapped. And by the way, multiplication is commutative, so the answer does not change even if the order is switched. So the area is still 20. Okay? So now that we just proved that the base areas are equal and the heights are equal, they tell you that the heights are 14. They're the same height. We can use Cavaliers' Principle to prove that these figures have the exact same volume. Here we go. What you need to say is this. The volumes of these two, I don't know what that was, of these two triangular prisms are equal. Because, and this is the Cavaliers' Principle part, because if two solids, or just a prism, two solids have the same height, move it up here, have the same height and same cross-sectional area at every level, then the solids have the same volume. Well, what in the world does that mean, Trevor? I will tell you. I basically just put that into words what I just said before. These two triangular prisms have the exact same base area. I said that here. It says, let's see. Okay, I said it a little differently. The same cross-sectional area at every level. So basically, if you just slice these at every single level, the areas are equal. Doesn't matter how you slice it, it's still equal. And the height is the same. So we know for a fact that these two prisms are equal, or equal in volume, by Cavaliers Principle. And that's how you do that question. Moving on to question number 28. Here we go. When volleyballs are purchased, they are not fully inflated. A partially inflated volleyball can be modeled by a sphere whose volume is approximately equal to 180 inches cubed. After being fully inflated, its volume is approximately 294 inches cubed. To the nearest tenth of an inch, how much does the radius increase when the volleyball is fully inflated? Okay, you need to set up two equations. I'm going to call this here, actually, first of all, you need to know the volume of a sphere. The volume formula of a sphere, which can be found on your reference sheet. I did that again. The volume of the sphere is equal to 4/3 pi r cubed. That is the volume formula of a sphere. Pretty important to know that. Now, what I'm going to do is I'm going to calculate the volume of the deflated volleyball. Okay? Well, the formula is still 4/3 pi r cubed. It doesn't matter. It's still a sphere. It's just deflated. Okay? So what I'm going to do is I'm actually going to find the radius because we're given the volume. Okay? If we're given the volume and we're given all these other constants, we need to find that radius. They want to know how much the radius increases by. So what I'm going to do is I'm going to take that 180 inches, which is the deflated volleyball. I'm going to plug it in to my formula. So 180, which is the volume, equals 4/3 pi r cubed. Your goal is to isolate this piece right here. You're trying to solve for r, not r3, but we're going to deal with that later. You need to solve for r. So the best thing to do is you need to multiply by the reciprocal of that. The reciprocal of 4/3 pi is 3/4 pi. Because the pi is really in the numerator. So you move it down to the denominator along with the 4, and you move the 3 up top. You just flip that fraction. And what you do to the one side of the equation, you must do to the other side of the equation. These cancel. Then I'm actually just going to leave this in its form. So if we take 3 times 180 and divide that by 4, you get 135, right? So this is actually 135 divided by pi. All I did, folks, I just simplified these numbers to make it a little bit smaller for ourselves, and I just smacked on the pi at the end. Equals r to the third. Now, this was a tricky question because if your geometry teacher did not tell you how to do this in your calculator, you probably got it wrong. You need to take the cube root of both sides. The cube root is similar to the square root, except it has an index of 3. So now, once we take the cube root of both sides, we're going to get an approximation. R is approximately equal to what? So, on the TI Inspire, let me get a clear document here. On the TI Inspire, your cube root button is Control, and you see the little up arrow here on the left-hand side? It says N radical X. That's what you want, because it has a little box here. I'm going to put a 3 there, and you're going to put 135 divided by pi. Your answer is 3.5026. So I'm going to round that to 1 decimal place. Just because there's a 0 there, it doesn't really matter. Or if you want to make it 3.503, that's fine as well. Actually, let me do that. 3.503. Okay, 3.503. Now what I'm going to do is I'm going to find the volume of the inflated volleyball. The radius of the inflated volleyball. So let's go ahead and set up that equation. The volume of the inflated ball equals 4/3 pi r cubed. Here we go. The volume of the inflated ball, they tell you, is 294. That equals 4/3 pi r cubed. We're doing the same thing here, folks. We're going to multiply by the reciprocal, 3 over 4 pi. 3 over 4 pi. That cancels with that and everything else. Take my word for it, when you simplify this by the coefficients, that will give you 441 over 2. That should be a 1, not a 4. 441 over 2 pi, and that equals r to the third. Now, from here, we are going to take the cube root of both sides again. Okay? And we get r is approximately equal to the following. So take the cube root of 441 over 2 pi. Make sure that you use parentheses, folks. That is not right. The pi needs to be in the denominator. You see how this calculator sometimes tricks you? You need to be very careful. That pi is supposed to be in the denominator. Your answer is 4.125. Approximately 4.125. Now, the question is asking you, how much does the radius increase? So what you need to do is you need to take this volume here, this radius over here, that 3.503, and subtract it from that radius. So I'm going to do that right now. So I'm going to take the big radius and subtract from the little one. So that's just going to be 4.12 minus 3.5. That gives you 0.622 when you plug that into your calculator. So it's asking you for the nearest tenth of an inch. 2 is not greater than 5, so the 0.6 stays. So your answer is the radius increases by 0.6 inches when inflated. And that, ladies and gentlemen, is a pretty tough part. In my opinion, that was a tough part 2 question. I did not think that was a fair question to give you on this exam. All right, moving on. Number 29. It says here, in right triangle ABC shown below, altitude CD is drawn to hypotenuse AB. Explain why triangle ABC, which is the big triangle, is similar to triangle ACD, which is this triangle over here. So there are 2 ways to do this problem. I will show you both. So the easy way you could do this is to actually just state the theorem that is associated with this. You could just state the theorem, or I'm going to show you another way. So the theorem states the altitude, which in this case the altitude is CD. The altitude to the hypotenuse, which the hypotenuse is in this case AB, the altitude to the hypotenuse of a right triangle forms 2 triangles that are similar to each other and to the original triangle. So that's the easy way, folks. That's just a basic theorem that you could have memorized, or you could kind of fudge your way through it, and you could, of course, use your own words. But that is the general theorem to prove why the green triangle is similar to the blue. Now, I assume many of you did not use that. Here's the other way that I think I prefer a little bit more than the theorem. Okay? I'm actually going to prove these 2 triangles by angle-angle similarity. That is your goal, to prove angle-angle similarity. Look at this, ladies and gentlemen. This angle A is reflexive in both the green and the blue triangle. In addition, angle C is a right angle because they tell you it is a right triangle. And we know that a right triangle has a right angle. And they tell you that this is the altitude. And remember that the altitude is perpendicular to its base, like we saw in the trapezoid construction. So this is a right angle. Well, clearly, these 2 triangles are proven by angle-angle similarity because the green triangle has this angle and this angle, okay? And the blue triangle has this angle and this angle to work with. So we're definitely going to prove it by angle-angle similarity. Here we go. So let me extend this page here. Here we go. As shown above, altitude CD is drawn to hypotenuse AB. Triangle ADC and triangle BDC are right triangles where angle ADC and angle BDC are right angles. All right, well, we just proved that just by the right triangle theorem and the altitude theorem. Right angles respectively. You don't need to write that respectively, but it would be nice if you would. Because an altitude of a triangle is drawn perpendicular to its base, forming right triangles. That is a long sentence, but it is a sentence. You could use symbols if you want to. You don't need to write words as well. Last but not least, angle A is reflexive. I'm just going to draw an arrow. Triangle ABC is similar to triangle ACD by angle-angle. And that, folks, is probably the easier of the two. I think that many of you would find that way to be a little bit better than the other way, but that is certainly a long explanation, but it is a doable explanation. All right, on to another toughie. Oh boy, here we go. This one was tough. I remember having some debates with the geometry teachers about this question, and we all couldn't agree on what the state wanted. The state accepted multiple answers. You could have picked any one of those. I'm going to show you actually two answers that you could have done, and one of it deals with a construction. Triangle ABC and triangle DEF are drawn below. Great. If AB is congruent to DE and AC is congruent to DF and angle A is congruent to angle D, write a sequence of transformations that maps triangle ABC onto triangle DEF. Ladies and gentlemen, when the question says sequence of transformations, they're expecting multiple transformations. It could be 2, it could be 3, it could be 4. Probably it's going to be 2 because this is a 2-point question. They want a point for one of the two. You get 1 point for one, and then you get the other point for the other one. So in this case, they're looking really for 2 transformations. So what we're going to do is I'm actually going to do the easier of the two first. First of all, you know just by looking at it, it looks like it turned. It's a rotation. Absolutely, it is a rotation. And then it's some sort of move. It's a translate. It's moving along the page. So we know it's a rotation and a translation. The problem is you can't just say rotation and translation. You will actually get no credit. What you need to say is the following. Rotate triangle ABC, which is this triangle over here, triangle ABC, clockwise about point C until DF is parallel to AC. Then translate triangle ABC along ray CF so that C maps onto F. That is one way. I'm going to actually show you what I'm talking about right now. So let's go ahead and talk about this. What I just said to you was this. I said rotate this triangle. I said rotate this triangle about the point C, which is down here. So you're going to rotate it clockwise this way until DF is parallel to AC. In other words, we want this line over here. We want this line to be parallel to this line over here. So spin it around, and we want DF to be parallel to AC. Then after that, we want to translate this triangle onto this triangle along ray CF, which is here. So basically what you're doing is you're drawing, let me just do a very rough sketch of this. I apologize for my drawing because I know it's not going to be good. That's disgusting. So what they're saying here is rotate it around, then you're going to push this up until point C maps onto point F. That's the easier of the two ways that I'm going to show you. Believe it or not, that was considered easy. I think that's very difficult. I think that's hard. The other way is the least popular way, and I remember I got a lot of, I don't want to say backlash, but I kind of do. I got a lot of backlash when I did the answer key to the Regents back when this test was administered, and people went berserk on this question. There's actually a petition floating around. It's pretty funny. But basically what I said for this is, wait a minute, I know, or I could see at least, that I could draw line CF and I could draw line AD. All right? And what I said is this. What if I draw a perpendicular bisector of CF? Right? What if I draw a perpendicular bisector? What would that do? Well, I'll show you. If you were to draw the perpendicular bisector, it would allow you to create a line of I'm going to change it to a different color. It will allow you to create a line of reflection right here. Okay? So what I'm saying here is reflect the triangle over the red line. Then after that, you are going to reflect, you are then going to reflect over the perpendicular bisector of line AD. So let me go ahead and draw that perpendicular bisector right now. So that is going to be the perpendicular bisector here. Okay. Draw a line here. This is a lot of work. Draw a line. There it is. So what I'm saying is reflect over those two lines and you map it onto itself. Okay? So flip it over the red line, which point C is going to be mapping onto over here in this vicinity, and then you just reflect it over again over the green line. So in words, how would you write that? Well, in words, you are going to say a sequence of transformations that maps triangle ABC onto triangle DEF is a reflection over the perpendicular bisector of CF, followed by a reflection over the perpendicular bisector of AD. That's how you put it into words, folks. And that is how you do that question. Either one of these two answers will be perfectly acceptable. You pick what you want to do. All right, number 31. Line N is represented by the equation 3x plus 4y equals 20. Determine and state the equation of line P, the image of line N, after a dilation of a scale factor of 1/3 centered at the point 4,2. Okay, first things first. I am going to put line N into mx plus b form. So your goal is to put this into y equals mx plus b form because we could work with this form. So we get 3x plus 4y equals 20. That's the line that they gave us. I'm going to subtract the 3x on both sides. We get 4y equals negative 3x plus 20. Okay? From here, I'm going to divide by the 4 on both sides. So we get y equals negative 3/4 x plus 5. Let's go ahead and graph that line. 5. Okay. So, if I were to go up to the y-intercept, that 5 is a y-intercept. 1, 2, 3, 4, 5. And your slope is down 3 to the right 4. Down 3 to the right 4. Down 3 to the right 4. And then just go in reverse. Up 3 to the left 4. And we could stop there. So what I'm going to do is I'm just going to simply create a line. All right, here we go. There's my line passing through all those points. Not too bad so far. Now it says determine and state the equation of another line that they don't give you, line P. The image of line N after a dilation with a scale factor of 1/3 centered at the point 42. Okay, it's centered at the point 42. Let's find the point 42, shall we? 1, 2, 3, 4, 1, 2. What is going on here? Ladies and gentlemen, the point 42 lies on the blue line. What does that mean? Well, it means that your dilated line is the same thing. Your answer was on the freaking paper. That's the answer. So what you have to say, and there's a reason why they say explain your answer. They're not dummies. They want to know why you know what it is. So here's your answer. Line P is actually the same line. 3x plus 4y equals 20. Well, the question is why? Here's your explanation. Since the line, I'm going to put that in parentheses, since line N contains the center of dilation the slope and the y-intercept remain unchanged. So if the center of dilation is on the line, the slope and the y-intercept remain unchanged, meaning it's the same line. And that's how you do that question. All right. In my opinion, that was tough. Okay. Are we moving on to the part 3s yet? Because this is taking a long time. Yes, we are. Okay, great. This one was actually a very, very easy part 3. In my opinion, easier than the part 2s. So, let's go ahead and graph these vertices. Triangle ABC has the vertices negative 5, 2, negative 4, 7, and negative 2, 7. And triangle DEF has the vertices 3, 2, 2, 7, 0, 7. Graph and label triangle ABC and triangle DEF on the set of axes below. All right, graph and label. So I'm going to go right to my graph page. And I'm going to graph the following points. I actually have the points right here. Negative 1, 2, 3, 4, 5, 1, 2. That's point A. Point B is negative 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And negative 2, 7. So that's B and C. So I'm going to connect those lines. Boom. Oh, sorry, those points, I should say. Boom, boom, boom. Okay, that's your triangle. Then it says you have another triangle, which is the point 3, 2, 2, 7, and 0, 7. All right? And that is the point, these points is labeled as D, E, and F. Okay? So now from here, I'm just going to connect those points like that. All right, so we just graphed and labeled. By the way, when it says label, yeah, you actually have to label the points as A, B, C, D, E, F. Okay, so from here on out, let's go ahead and answer the questions. We should get full credit here. Determine and state a single transformation where triangle DEF is the image of triangle ABC. They want to know, how do you get from here to here in one move? One move. Well, it's clearly a reflection because, again, orientation has changed, and it is a reflection over the vertical line x equals negative 1. And one thing that I see in many geometry students is they lack the knowledge of graphing vertical lines. This is the vertical line x equals -1 because every single x value on this line is -1. If you just plot a bunch of ordered pairs, this is the point -1, 0. This is the point -1, 4. This is the point -1, 10. All the x values are -1. That's why that line is called x equals -1. So let's go ahead and put that into words, right? Determine and state a single transformation. A single, I don't want to put this in a complete sentence, but I have to. A single transformation that would map triangle ABC onto triangle DEF is a reflection over the line x equals -1. That is how you explain your answer. Now it says, for the follow-up question, use your transformation to explain why these two triangles are congruent. Why are these two triangles congruent? This is on every freaking geometry reading. Make sure that you know it. This is a reflection. It's a rigid motion. And remember that rigid motion is a fancy term for preserving everything. Size doesn't change. Shape doesn't change. Angle measure doesn't change. Area, perimeter, everything remains the same. It's an identical copy of what you have in front of you. So your answer is triangle ABC is congruent to triangle DEF because a reflection, because we are reflecting, a reflection is a rigid motion which preserves distance and congruency. Make sure that you use big boy and girl words. Do not say preserve size and shape. It doesn't sound good on the Regents, even though that you might get full credit. You're really not supposed to because we are in 10th grade or 9th grade if you are accelerated, or even 8th grade. You're supposed to say distance and congruency. We are big boys and girls now. Advance your vocabulary. And that's how you do question number 32. Number 33, a basic proof. Here we go. Given RS and TV bisect each other at point X, and TR and SV are drawn, prove that TR is parallel to SV. So first things first, I am going to draw myself a 2-column proof. And yes, on the Regents, they will not give you the 2-column proof. You actually have to write it in yourself. All right, so I'm going to put in statements, and I'm going to put in reasons. Okay. Statements and reasons are in. Let's do it. Here we go. Let's start labeling the bejesuses out of this diagram. So RS and TV bisect each other. That means that TX is congruent to XV and RX is congruent to XS because X is a midpoint of both of them. Then we just have vertical angles are congruent. I'm going to call this angle 1 and angle 2. Your plan to prove these two triangles to be congruent is by side, angle, side. That is the plan in order to get this question right. There is no other possible way that you could prove these two triangles to be congruent. It has to be side, angle, side. If you wrote something else down on your paper, which I hope you did before watching this video, that it has to be side, angle, side. It can't be anything else. So let's go ahead and solve this proof. Here we go. So I'm going to write all my given information. RS... And I'm actually just going to write I'm just going to write all the givens. RS and TV bisect each other at point X. And then I'm going to say TR and SV are drawn. Your reason is given. Do you have to include the givens in your proof? Of course you do, or else you lose credit. So make sure that you write the givens, which I think it's stupid because even if you write the givens, you get no credit. But if you don't put the givens, you lose credit. So make sure that you write the givens. All right, number 2. I want to prove that those two pairs of line segments are congruent to each other. So RX is congruent to XS and TX is congruent to XV. Before saying that, though, you need to state that X is a midpoint, okay? So I'm going to say that X is the midpoint of TV and RS. I should be watching TV right now. Number 2, I'm going to say that a bisector is drawn to its midpoint. Do you need to include this step? Honestly, in my opinion, it's still up in the air. When I was in geometry, I never wrote that X is midpoint. I just went right for these congruencies, and then I just said that a bisector divides a segment into 2 congruent parts. That's fine in my opinion. I don't know why Common Core is making us do this, but we have to do it anyway. But we, got to suck it up and deal with it. So now, since I just proved that that's a midpoint, I can now say that TX is congruent to XV, and I could say that RX is congruent to XS. And your reason is a midpoint divides a segment into 2 congruent parts. Okay? Number 4. And by the way, I just proved those lines to be congruent. So your side and your side are done. Now we just got to prove those angles. Here we go. I'm going to say that angle 1 is congruent to angle 2. My congruent sides are disgusting. Number 4, your reason, vertical angles are congruent. Okay? Number 5, we just proved everything that we needed. Side angle, side. Here we go. We're going to say that triangle TXR is congruent to triangle VXS. Your reason is side angle side is congruent to side angle side. Number 6. Now, here's the problem. They're not asking you to prove these 2 triangles to be congruent. They're asking you to prove that TR is parallel to SV. Well, how do we prove that? Well, you should remember, in order to prove parallel lines, you need something like alternate interior angles that are congruent, alternate exterior angles that are congruent, corresponding angles are congruent, or same side interior angles are supplementary. We have to go with alternate interior angles are congruent because we're dealing with triangles. We're talking about the insides of the triangles. So I'm going to label these 2 angles, which are corresponding to each other, as angle 3 and angle 4. So number 6 is going to be that angle 3 is congruent to angle 4. Well, why did I just prove that? By CP/CTC, corresponding parts of congruent triangles are congruent. Basically saying if you have 2 identical copies of the triangle, everything that's corresponding to each other is equal to itself. Last but not least, number 7. TR is parallel to SV. Why? Well, it has to do with angles 3 and angle 4. So, I'm going to say this, and here's your theorem that I hope is drilled into your head. If a pair of alternate interior angles are congruent, then the lines that are cut by the transversal, which is just a line, are parallel. Done. And that, ladies and gentlemen, is how you do that proof. Honestly, it could have been worse. It could have been worse. That is your proof. All right, we're getting closer to the part 4s of this exam. This test is taking forever. Okay, here we go. Last part 3. This one was interesting. Number 34. A gas station has a cylindrical fueling tank that holds the gasoline for its pumps and modeled below, as modeled below. The tank holds a maximum of 20,000 gallons of gasoline and has a height of 34.5 feet. A metal pole is used to measure how much gas is in the tank. We don't want that to overflow, right? Because it will cause a fire, right? To the nearest tenth of a foot, how long does the pole need to be in order to reach the bottom of the tank and still extend 1 foot outside the tank? Justify your answer. And remember that 1 cubic foot is 7.48 gallons. Ladies and gentlemen, they do not give this information to you just because they just decided to give you information. No, you have to use that information to get the answer right. And this is how you need to do it. This is how. You need to figure out, let's see, we're trying to find the length of the pole. Well, you need the radius or no, I'm sorry, you need the diameter, and then this is an extra 1 foot, okay? So it says here, the tank holds 20,000 gallons and has a length of 34.5 feet. Yeah, okay. So this has a length of 34.5 feet. Well, ladies and gentlemen, what does holding gallons have to do anything with a cylinder? By the way, this is a cylinder because it says it. Well, what should be popping in your head right now, screaming to you, is volume. You need to use the volume formula of a cylinder to get the radius, then eventually the diameter, then eventually the answer. So the volume of a cylinder is pi r squared times the height. The problem is, here's our problem, folks. We have the height, we don't have the radius, and we don't have the volume. But we can get the volume. Why? Because they tell us how many gallons are in this freaking thing. It's 20,000 gallons. So what we need to do is we need to convert gallons to cubic feet, okay? Because you can't just plug in 20,000 as your volume. That makes absolutely no sense because you're working with different units. You're working with feet and you're working with gallons. You need to convert gallons into feet. Are you in the picture so far? I hope so. I hope I just explained that well because I was going on a rant there. So here we go. We're going to take 20,000 gallons and we're going to multiply that. Sorry, gallons. We're going to multiply that by 1 foot cubed divided by 7.48 gallons. And listen, I get it. Conversion factors are not people's favorite things, but I hope to make it easier for you. Your goal is to cancel out the gallons in the numerator and the denominator, and you're left with feet cubed on the top. That's your goal. So in this case, you're just taking the fraction, you're multiplying it by the 20,000. So go to your calculator. 20,000 multiplied by 1 divided by 7.48. And that gives you a result of 2,673.797. Okay. So 2,673.797 feet cubed. Ladies and gentlemen, what is this? What is that? That's the volume of the cylinder in terms of feet. So we just found the volume. Happy face. Yay. Now let's find the radius. Here we go. Plug in the information. Volume equals pi r squared times the height. The volume is 2,673.797 is equal to pi r squared times the height, which is equal to 34.5. Let's isolate r and solve it. We need to divide by pi and the 34.5 on both sides. So we need to divide both of those. So pi times 34.5. Pi's cancel, 34.5 cancels. When you plug this into your calculator, just take my word for it. I don't want to type that in. You get 24.66944,789.46. Yes, leave it in that number. Equals r squared. Now to solve for r, you just simply take the square root of both sides. And you get r is approximately equal to 4.966834976. No, I'm sorry. Hold on a second. Let me back it up. 96683479639. Okay, folks. This is your radius. Now let's find the diameter. What is the diameter? Well, the diameter is just you're multiplying the radius by 2, or you're adding it twice to itself. So the diameter is equal to this. 9.93366959277. That is the diameter. Now, we're almost there. We're trying to find the length of the pole. We just found this piece that's inside the tank. Remember that there's a 1 foot extension, because if you drop it in without a foot extension, it's going to get stuck in the tank. You need something to pull it out with. So, we just need to add 1 to that number. All zeros at the end. Add that up, we get 10.933. They want it to the nearest tenth of a foot. That, ladies and gentlemen, is 10.9 feet, and that is the length of the pole to the nearest tenth of a foot. Man, was that challenging. I thought that was a ridiculously difficult question for that one. finally on to the part 4s. Now, the part 4s are going to take me freaking forever. Part 4s. Here we go. Okay, this question, you take the 6 points and you run with it. It's that simple. Quadrilateral PQRS has the vertices -2, 3, 3, 8, 4, 1, and -4, -1, -4. Prove that PQRS is a rhombus. What you need to know is that a rhombus has 4 congruent sides. That will help you a lot to get this question right. So here's our plan. The plan is use the distance formula 4 times to prove that all sides are congruent. So you need to use the distance formula. You got to know what the distance formula is. So what we're going to do is we're going to find the lengths of PQ. We're going to find the length of QR. We are going to find the length of RS. And we are going to find the length of PS. Here we go. The distance formula is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. I'm not going to write this formula each time just because I wrote it once. That's all you need to do. I'm going to plug in the coordinates to solve it. So here we go. The distance is equal to the square root of 3 minus a -2 quantity squared plus 8 minus 3 quantity squared. That continues on to give you an answer. 3 minus a -2 gives you 5. Square that. 8 minus 3 is 5. Square that. You get the square root of 25 and 25. That gives you the square root of 50. Leave it as is, folks. Do not simplify that radical. That's just dumb. So keep on going with this. Here we go. Finding the length of QR. Let me do it in a different color so you don't get confused. D equals the square root of, take your coordinates and plug them in. 4 minus 3 squared plus 1 minus 8 squared, which gives you the square root of 1 squared plus a -7 squared, which gives you the square root of 1 plus 49, which is equal to the square root of 50. Leave it as is. So far, we're doing good. We have 2 sides that are congruent. Let's prove the other 2 sides are congruent as well. D equals the square root of 4 minus a -1 quantity squared plus 1 minus a -4 quantity squared. Simplify that a little bit more. You get 5 squared plus 5 squared, which is equal to the square root of 25 plus 25, which is equal to the square root of 50. Leave it as is. Moving on to the next one. Hope I'm not monotone. I'm getting bored with this question. Last but not least. -2 minus a -1 quantity squared plus 3 minus a -4 quantity squared. A lot of work for just the distance formula. That gives us 5 squared plus 5 squared, which is equal to the square root of 25. Wait a minute. 2 plus... No, I'm sorry. That's a -1. My apologies. Back it up. I don't know what my adding was right there. I don't know what that was. That's the square root of -1 squared plus positive 7 squared. That gives you the square root of 1 plus 49, which is equal to the square root of 50. Oh, perfect. We got 4 sides that are congruent to each other. Fantastic. Now, unfortunately, you need to actually write a sentence to prove your reasoning. So the conclusion, you actually need to draw yourself a conclusion. The conclusion is, since all 4 sides are congruent, quadrilateral PQRS is, in fact, a rhombus. Beautiful. Okay, so that's how you do the first part. Then there's another part, so let's go and do that one. Then it says, prove that PQRS is not a square. Now, this is what differentiates a rhombus from a square. A square and a rhombus are different because a square has congruent diagonals, a rhombus does not. So what your plan is, we're going to use the distance formula again. So your plan is to actually use the distance 2 times on the diagonals of the rhombus. That would be sufficient information to prove that this is not a square. So the diagonals in this case, if we were to just draw PQRS, let me just draw it on the grid here, just so you know which diagonals you're talking about. This is -2, 1, 2, 3. Hold on one second, folks. I should have done this earlier, but I didn't. R is 1, 2, 3, 4. 1, 2, 3, 4, 1. And S is down here. Okay, so this is PQRS. So we're talking about diagonals PR and QS. Okay, PR and QS. We're trying to prove that these two diagonals are not, and clearly you could just tell off my disgusting diagram that those two diagonals are not congruent to each other. So we're going to solve for PR, and we're going to solve for QS by using the distance formula. So D equals the square root of 4 minus a -2 quantity squared plus 1 minus 3 quantity squared. We get the square root of 6 squared plus -2 squared, which is the square root of 36 plus 4, which is the square root of 40. Okay. QS, D is equal to the square root of 3 minus a -1 quantity squared plus 8 minus a -4 quantity squared. D equals the square root of 4 squared plus 12 squared, which is the square root of 160. Those, folks, are not the same radical. Therefore, the diagonals are not congruent to each other. So your conclusion, because we do need to draw a conclusion, your conclusion is the following. Since the diagonals are not congruent, rhombus PQRS is not a square. And you are done with that question. Honestly, not too bad. So now what we're going to do is we are going to talk about the final question of this exam, which had a lot of people kind of pissed off about this. This is Frida, and Frida is probably in air traffic control. Let me read you the question and explain what is going on. Frida, who is training to use a radar system, detects an airplane flying at a constant speed and heading in a straight line to pass directly over her location. She sees the airplane at an angle of elevation of 15 degrees and notes that it is maintaining a constant altitude of 6,250 feet. 1 minute later, she sees the airplane at an angle of 52 degrees. How far has the airplane traveled to the nearest foot? And if you don't know that this is strictly a trigonometry question, you are either sleeping or really confused. Probably you're really confused. So, but if you got it, great. I'm actually going to search for a plane because I am a horrible drawer. So I actually want to find myself a airplane. Let's see. Which one's good? That one will do. A Boeing 737 aircraft. Sweet. Okay, I'm going to shrink this down here. That is god awful. Shrink it down, and we're gonna, nope. And I want to flip this. Flipped it left to right. Awesome. Nice, we got 2 airplanes. So, let's go ahead and draw ourselves 2 triangles. Well, how do we do it? Or how do we draw the diagram? So that, in my opinion, that was the hardest part of this question, to get the figure going and draw it. So basically, there's an airplane at a starting position, and the height is 6,250 feet in the air. Okay? It's traveling in this direction. The plane then all of a sudden is over here when Frida observes it yet again. So that means that it is still the same height, it just traveled a distance. Doesn't matter, right? Now, these are where your 2 triangles come in, folks. Right there, those are your 2 triangles. So these are both right angles. So the plane traveled from here to here. I'm going to call this distance x. All right, I'm actually going to highlight this. I'm going to call this distance x. I'm going to call this distance and this distance 2 different letters. I'm going to call this y, and I'm going to call this z. And you'll see why in a moment. The little angle, the little baby angle, is 15 degrees, and the big one is 56 degrees. Okay? So how do we do this? Your goal in essence is to get this here. But we need to use the pink and the blue highlighting marks to get x. So this is what we're supposed to do. To solve for x, we need to do the following thing. Take x is equal to the letter z, or whatever the length of z is, and subtract y. The problem is we don't know what z and y are. We have to use that by using trigonometry. Let's go ahead and do it. I'm going to shrink this down because it is taking up a lot of room. Okay, not too bad. So what I'm going to do is I'm going to take, or first things first, I'm going to write down a Sohcahtoa because I know I'm working with it. Okay. So in reference to the little angle 15 over here, we're given 6,250. That is called your opposite side of that triangle. The side next to it, which is your z, is called the adjacent side. We're using O and A. That means that we're using tangent. So what we're going to do is we're going to solve for z first. So I'm going to take the tangent of 15 degrees. That equals the opposite side, which is 6,250 feet, divided by the letter z. I don't know what z is. I'm trying to find that out. So we're going to cross multiply. So we get z tangent of 15 is equal to 6,250. To solve for z, you're going to divide by the tangent of 15 on both sides. And we get z is approximately equal to, now when we plug this into our calculator, make sure your calculator is in degree mode. When you plug this into your calculator, you get the following. So control division, 6,250 divided by the tangent of 15 degrees. Make sure your calculator is in degree mode. We get 23,325.318. I'm going to round that off. So z is approximately equal to 23,325.32. That, ladies and gentlemen, is the distance in feet from here to here. That is this whole distance, okay? So now what I'm going to do is I'm going to use the other triangle. I'm going to use the other the smaller triangle to calculate what the distance is for y. All right, so let's go ahead and do that. Sorry for my sloppy handwriting and my highlighting business. That's not working right. Okay, I don't know why that's not working. Whatever. All right, so again, we're using tangent, opposite, adjacent. Adjacent side is actually this now, the little guy. Adjacent, and this is still, okay, this side is still 6,250 feet because it's maintaining its altitude. Okay, so let's go ahead and solve for y. Let's go ahead and solve for y. So we're using tangent still. So now it's just a different degree measure. The tangent of 52 is equal to 6,250 feet over y. Cross multiply and solve. Y tangent of 52 equals 6,250. Divide by the tan of 52. Divide by the tangent of 52. Tan of 52's cancel. When you go to your calculator, control division, 6,250 divided by the tangent of 52. You get 4,883.04. So y is approximately equal to 4,883.04. Okay, now remember what I said before. So you need to solve for x. To solve for x, you take z and subtract y. So we're taking 23,325.32 minus the 4,883.04. Your goal is to try to find the distance traveled from this point to this point. So when you plug that into your calculator, just take my word for it. You get an answer when it's rounded to the nearest foot. You get 18,442 feet. Ladies and gentlemen, that is the length of x, the distance that the plane has traveled from point A to point B. Okay? That's how you do the first part. Then, all of a sudden, they throw a ridiculous part on the exam, which to this day I'm still pissed off about. Determine and state the speed of the airplane to the nearest mile per hour. And if you're getting anything above 500 miles an hour, or if you're getting negative numbers, the plane will either fall out of the sky or go to Mach 1 and Mach 2, the speed of the Concorde and the spaceship. And if you don't know what the Concorde is, look it up. It's a pretty magnificent aircraft. So determine and state the speed of the airplane. So you should know from Algebra 1, believe it or not, and a lot of knowledge is from Algebra 1, speed is equal to distance over time. Now, if you're thinking, Trev, I thought it was the change in distance over the change in time. You're thinking of average speed. Okay, speed is just distance over time. So the speed, well, we got to find the distance. Oh, we got a problem here, folks. Oh, they were nasty. Miles per hour. Huh? Miles per hour. Trevor, my answer is in feet. I got to convert to miles. And in addition, where is it? 1 minute. Minutes is not an hour. So you need to convert minutes to hours. Unbelievable. Are they sick? And I swear to God, New York State is crazy. So we need to convert. You can't get this question right unless you convert. So let's convert the feet to miles first. Well, from your reference sheet, this is all found on your reference sheet. You just need to know how to do it. We're just going to take 18,442 feet, and we're going to multiply it by 1 mile, and there's 5,280 feet in 1 mile. You see, again, the conversion factors, that the feet cancel on the top and the bottom, and you're only left with miles. That's your goal. So I'm going to go to my calculator. 18,442 divided by 5,280 feet. Your answer is, all right, I need to simplify that, 3.49. Okay, so that is approximately equal to 3.493 miles. Now, the second thing that you need to convert is minutes to hours. Honestly, you don't need a conversion chart. Honestly, I don't even think that the conversion chart has minutes and hours on here, does it? No, it does not. So you need to use your everyday smart life skills to know that there are 60 minutes in an hour. And I'm sorry, if you don't know that there's 60 minutes in an hour, you have been sleeping all your life. So, I mean, 60 minutes is a show name, okay? 60 minutes is 1 hour. So 1 minute is equal to 1/60th of an hour. Okay, that's what you need to do. So I'm going to take this information and this information. I'm going to plug it into my speed formula. The distance is 3.493 miles, and we're dividing 1/60th of an hour. I'm going to go to my calculator. Here we go. Control division. 3.493 divided by, complex fraction here, 1/60. You get an answer of 209.58. You need to round it to the nearest mile per hour. The aircraft is traveling at a speed of 210 miles per hour because we have to round that up. And that, ladies and gentlemen, is the answer to that question. I hope that this was helpful. Make sure that you hit that subscribe button down below and visit my website at www.nysmathregentsprep.com for much more math content and geometry and further mathematical subjects in your high school future. And I hope to see you soon.